Let's talk about power and type 2 error. Let's suppose we have a company that has customer service representatives on phone lines so that customers can call in. If our customers are waiting on average more than 90 seconds, we may frustrate them and start to lose customers and lose business. So we want to do a test. We want to do a hypothesis test to test the claim that the mean wait time for a customer service rep is more than 90 seconds. If we reject it all in favor of the alternative, we are going to believe that this is true, and we are going to hire more representatives to staff our phone lines. All right, now, if the null is true, we're going to assume the mean is equal to 90. That is the sampling distribution we're going to use to run our hypothesis test. If the alternative was true, then the real sampling distribution would have some mean average above 90, and it would look like this. We want to get used to this two-way table to describe what happens or how a type 1 and type 2 error can occur. If in our hypothesis test we go with the alternative, but the null is true, then we made a type 1 error. So in other words, if we take a sample and we get a sample mean up here somewhere, and it's extreme enough that we don't attribute it as being due to chance, we're going to reject the null and go with the alternative. But if the null is really true, and that just happened due to chance, we just made a type 1 error. The consequence is we're going to hire more people when we didn't need to, so we'll lose money in that regard. That is a type 1 error. The null was true, but we went with the alternative and we were wrong. So a type 2 error is when the alternative is true, when maybe the true sampling distribution looks more like this up here. And we went with the null in our hypothesis because perhaps we got a sample mean down here. It might have been above 90, but it wasn't extreme enough for us to be convinced that the alternative was true. It wasn't beyond a reasonable doubt. Well, we would go with the null, but we'd be wrong. We'd be making a type 2 error. So if the alternative was true, the mean was really above 90, but we got a fairly unusually low sample mean, which when we were running the test caused us to fail to reject the null, then we failed to conclude the correct idea, which was that the mean wait time is more than 90 seconds. So if the alternative was true, but we went with the null in our hypothesis test, we made a type 2 error. The implication or consequence of that error is that we thought everything was okay, that the mean wait time was 90 seconds, but in reality it's more than 90 seconds. We should have hired more people. The consequence is we're going to start to lose business. We're going to lose customers and lose business. So those are the two big errors. And then the power of the test is if the alternative is true, and in our hypothesis test we conclude that the alternative is true, we made the correct decision, and that is the power of the test. So we want to be able to run a powerful test to detect if this is really true, that the mean average wait time is more than 90 seconds, we want to detect it. So we're hoping that we get a sample mean up here, and that would be more likely if the alternative was true, we would correctly reject the null. All right, now let's go with the z-test for means. Let's just assume that we know the population standard deviation, that it's 50 seconds, and we take a sample of 25 and the population is normal. That would mean that the standard deviation of our sample means is 10 seconds. So if we look at our sampling distribution where the null was true and the mean is really 90 seconds, if we go 3 standard deviations in each direction, we trap out 99.7% of all sample means, and we get this situation right here. Now here's what we want to know. If we're going to run this at an alpha level of 0.05, significance level of 0.05, we should recall that the z-score that traps 5% of the tail is 1.645. That means that if the null is true, as long as we get a sample mean that's at least that many standard deviations beyond the mean of 90, we're going to be in the critical region where we will reject the null. So one of the first things we need to know then is, what's this critical sample mean value? What would the sample mean have to be so that you would end up being exactly 1.645 standard deviations above the mean? Well, that's an easy algebra situation. There's our z-score formula. If we plug in that desired z-score and we're trying to solve for x bar with a known mean of 90 and a standard deviation of the sample means of 10 seconds, then we can calculate that the critical x squared, rather, the sample mean, the critical sample mean where we would reject the null would be at 106.45 seconds. So if we reconstruct this, if we draw our normal distribution where the null is true, there's where the critical region begins at 106.45 seconds. If we get a sample mean above that, we're going to reject the null. Now the way we would have to calculate the power of the test is somebody would have to recommend a particular mean average wait time when the alternative is true. So suppose the CEO says, okay, you guys, if the true mean wait time was 110 seconds, is your test powerful enough for us to reject the null and correctly accept the alternative, or do we run the risk of making a type 2 error? So we want to find the probability of a type 2 error against the alternative that the mean would be 110. So here's 90, the mean of the null. Here's where 110 would be. We're now going to presume that the true mean is really 110, and this would be the cutoff for where the critical region would start given this hypothesis test. So if we overlap these two sampling distributions, the green one would be the null, that the null is true. We're assuming that the mean is 90 seconds. So the green distribution is the sampling distribution we would use to run the test. The null would be assumed to be true. And this red shaded region then would be the critical region, that region above that 106.45 seconds where our sample mean would have to exceed that in order to be in the critical region and reject the null and go with the alternative. Then I've drawn this blue distribution. I'll keep using blue for the alternative and green for the null. We have to be given some supposed mean that is within this constraint. So we're going to say, suppose the true mean is 110, so this is our alternative. Okay, so that would be the sampling distribution we'd actually be sampling from. So this gets pretty abstract. It's double abstraction. So here's the deal. We're going to be running the test where the mean is assumed to be 90, because that's what the null says, but we're going to be sampling from this true sampling distribution where the mean would be 110. So you can see if the blue distribution is reality, there's a pretty good chance that we're going to get a sample mean up in here somewhere, so that when we're running the green hypothesis test, we would exceed that sample mean that we need to exceed in order for us to correctly reject the null and accept the alternative. We have to exceed that 106.45 seconds. So we set it up this way. We recall that the sample mean for the standard deviation for the sample means would be 10 seconds. The green is the null hypothesis that we'd be assuming to be true. The blue is now what we're saying is, hey, suppose the true mean really is 110, so that's where you will be sampling from. All right, so then the probability of a type 2 error would be, given that the mean is 110, so given that the true sampling distribution would have a mean of 110 seconds, that's reality for our business and our customers, is that they'd be waiting on average 110 seconds. Well then, how likely is it that you'd have bad luck and you would get a sample mean below the 106.45, causing you to fail to reject the null? Well, we could do a normal CDF for that. We can type in the numbers and we would get 36%. So here's the deal. In this distribution that we'd be sampling from, where the mean was 110, the likelihood that we would actually get a result below what we need to get in order to reject the null and go with the alternative, that would be 36.13%. That's the probability of a type 2 error. Meanwhile then, if the mean really was 110, if there's a 36% chance of getting a result that's too low to reject the null, then it must be that 64% of the time, 1 minus that, 64% of the time, we would be getting sample means that are large enough that we would reject the null in this hypothesis test and correctly go with the alternative. So again, the probability of a type 2 error is, given that the true mean is 110, this blue distribution right here, what's the likelihood that you go into that sampling distribution, take a sample of 25, but you end up, just due to bad luck, getting a sample mean that's down here? If that happens, if you get sample means that are down here, then your conclusion in the hypothesis test, seeing as you didn't make the critical region, is that you would fail to reject the null, stick with the null hypothesis, and be wrong with your conclusion that the mean is 90. So here's a picture of it. The power of the test is going into this blue distribution and getting a big enough sample mean so that you can reject the null. And if the alternative really is true, the blue is really reality, if we get a big enough sample mean up here, we're going to correctly go with the alternative in our hypothesis test. That's the power of the test. We made the right decision. But if, on the other hand, the alternative is true, look at me color coding, this is awesome. If we color code here, if the alternative is reality, if it's true, and this blue sampling distribution is reality and where we're sampling from, there exists the possibility that due to bad luck, due to chance, we can end up getting a sample mean that's down here somewhere, causing us in our hypothesis test to fail to reject the null, stick with the idea that the mean is 90, that would be a type 2 error. So type 2 error is when the blue distribution is true, when the alternative is true, that we got a small enough sample mean that we failed to reject the null, that would be making a type 2 error. That's that area under the curve. That was that 36%. But if the alternative is true, again, this blue distribution is true, and we get a sample mean that's above that 106 minutes, or 106 seconds, then we're going to correctly reject the null, and in our test, we're going to go with the null, or reject the null and accept the alternative, and that would be the power of the test. We'd be making the correct decision, and so that would be considered the power. So one of the things to consider is that the total probability here is 1. That if the type 2 error has a probability of 0.36 of happening, then the power would be 0.64. So these two probabilities would add up to 1. So again, it's a conditional probability. If the alternative is true, what's the probability that we would get a sample mean that's too low? That would be the probability of a type 2 error. And by the way, this is referred to as the beta of the test. Beta is the probability of a type 2 error. Then we go back over here. Well, what if instead reality was the green distribution? So the null was true. If the reality is the green distribution is true, the null is true, then if we get a low sample mean in our sample, if we get something down in here, then we are going to fail to reject the null in our test. We'll stick with the null. That would be the correct decision. But if the green distribution is true, if the null is reality, if the green distribution is true, if just due to random chance we get a sample mean up here that's somewhere in the critical region, then in our test we're going to reject the null and go with the alternative, but that would be a type 1 error. We would be thinking that the alternative was true because we got an extremely high sample mean, but it was just due to random chance. The green distribution is true. We made a type 1 error. This is called the alpha level of the test. Type 1 error is alpha, type 2 error is beta. And remember, the type 1 error is if the null is true. If the null is true, then the probability of us getting a result at least as extreme as the one that we got is the probability of a type 1 error. That's the alpha level of a test. So how can we increase the power of the test? We can increase it by decreasing the intersection of the null and the alternative. So if we increase the n, recall that the standard deviation then of the sample means, it was 50 divided by the square root of 25. Maybe we increase the sample size to, let's say, 100. Now the standard deviation of the sample means would be 50 divided by 10. The standard deviation would only be 5. So both of these sampling distributions would be much less spread out. They'd have less variability. They'd hardly have any overlap, any intersection. So now you can see if the alternative was true, the likelihood of us getting sample means in the region that would cause us to reject the null when using the green distribution, that would be very high. So the power of the test would be high. Probably the type 2 error would be really low. So if we increase the sample size, it's a more powerful, more accurate test. And so it shrinks the spread of the two distributions, and there's not much overlap. That reduces the probability of a type 2 error and increases the power of the test. We could also go over here, we could widen the gap between the two, between the mean of 90 and the mean of the alternative. If we say, you know what, what's the power of the test if, let's suppose, the mean is 150 seconds? Well, then those would be our sampling distributions, and there'd be like no overlap at all. And if that was reality, if we were really sampling out of that population there, that sampling distribution, there'd be no chance of a type 2 error, basically. So the power of the test would be 100%. So the idea is, if you can widen the gap, if you can reduce the overlap of these two sampling distributions, then you increase the power of the test. That's fairly arbitrary, going up to 150. Usually something like 110 is important to the business. They've come up with that number. They didn't just snatch it out of the air. So they said, look, if the mean is as high as 110 seconds of wait time, we need to do something. So will your test be able to detect it? So the best way to increase the power of the test is to increase the sample size. The last way that we can manipulate and increase the power of the test is to actually increase the alpha level. Us being willing, let's say, to live with a 10% chance of making a type 1 error. If we increase the chance of a type 1 error, we decrease the chance of a type 2 error, and both of those are, both the type 1 error and the power are inversely proportional to the type 2 error. So increasing type 1 error decreases type 2 error and increases the power of the test. And you can see that here. If instead of having our cutoff being over at 106 minutes, if we could bring it back to like 102 minutes, then there's a greater chance that we're going to get a sample result, a sample mean, that would put us in the critical region, and it would increase the power of the test, and it would reduce the type 2 error. So that's an explanation mathematically of how the power is increased and how to calculate power and type 2 error. But here's the good news. What must we really know in AP statistics with regard to type 2 error and power? Well, number one is just know the implications of the two. Type 1 error, type 2 error. So here it is. Remember our situation right here. If the people are really waiting a long time on the phone and we don't do something about it, we're going to lose business. So if we fail to reject the null in that case, we fail to accept the reality that the mean is greater than 90, then we would be making a type 2 error. And the consequence of a type 2 error is, hey, we thought the null was true. We didn't think we needed to hire any more people, so we didn't. So we're going to lose business, and that's the more costly of the two mistakes. The type 1 error is when the null was true, but we got an extreme enough result that we thought the alternative was true, so we went ahead and hired more people. But hold the phone, we didn't have to. So in that case, we would have gone to the expense of thinking this was true and that we needed to hire and train more people, when in reality we didn't. So we won't be losing customers, we won't be losing business, but we will go to the expense of spending money on more employees. So you need to know the implications or consequences of type 1 and type 2 error and be able to answer the question which one is more drastic, is the worst of the two errors. And then you'll need to know how to increase the power of the test. And again, if you have to, just memorize it. If you want to go back through this video and say, well, I think I can make sense of this as to why it is that if we increase the sample size, we'll increase the power of the test. Remember that by increasing the sample size, what it does is it narrows the two distributions down, and so there's almost no overlap. And so the likelihood is that you're going to go into the true distribution, sampling distribution, and you're going to get sample means that are plenty big enough to cause us to reject the null when running the test that's here. So an increase in the sample size will widen the gap between the two sampling distributions and decrease the overlap, the intersection. It's going to make it a lot easier for us to correctly reject the null, making it a more powerful test, reducing the type 2 error. If we increase the alpha level, that's when we're saying, excuse me, that's when we're saying that instead of setting the alpha level way out here, we can pull it back. We can make sure that our rejection region is back further, and so we eat away at some of the type 2 error that we used to have and give it to the side of the power of the test, and now the type 2 error is reduced down to a smaller amount. So if we increase the alpha level, we're increasing our likelihood of making a type 1 error, which decreases the likelihood of making a type 2 error, which increases the power of the test. Lastly, we can increase the gap between the mean proposed for the alternative and the mean of the null, which in our case was 90, but this is a little bit more arbitrary. These are the two guys you really want to memorize. Make it a more powerful test, increase the sample size. Decrease your probability of a type 2 error, which is beta, by increasing your acceptance in making a type 1 error. That will get the job done as well. And then finally, you might be asked to mess with some probabilities involving the concepts, but the question would pretty much walk you through the process to where you wouldn't have to construct it all on your own. It might look something like this. The experimenter set a sample mean of 106.45 seconds as the threshold for accepting the alternative, in other words, rejecting the null. And so if the experimenter just happened to be sampling from a population where the mean customer service wait time was 110 seconds, then find the probability of rejecting the null. So you would go to that distribution of 110 and find the probability of getting a result above 106.45. That's the power of the test. That's answering the question right there. So, tough concept, but not impossible to comprehend. And the more you can understand it, the easier you're able to answer questions involving the concepts.